Today I would like to discuss about the preparation of alkyl halides. I would like to discuss about the preparation of alkyl halides. So the one of the preparation is alkenes reacts with halogen in presence of sunlight or at high temperature or at a suitable catalyst to give alkyl halide. Alkyl halides are obtained by treating alkenes with halogens in presence of sunlight or at high temperature or at suitable catalysts like copper chloride, ferric chloride, or ferric bromide to give alkyl halides. Alkyl halides. Alkenes reacts with chlorine or bromine in presence of sunlight or at high temperature or using suitable catalysts like copper chloride, ferric chloride, or ferric bromide, etc. to give alkyl halides. Let us take an example. Methane is reacted with chlorine in presence of UV radiations to form methyl chloride. Methyl chloride. When you see the mechanism here in the first step, the chlorine absorbs the UV radiation. The chlorine absorbs the UV radiation and undergoes homolytic cleavage and forms a radical. The chlorine absorbs the UV radiations and undergoes homolytic cleavage and forms the radicals, halide radicals forming. These halide radical is reacted with alkane and forms alkyl radical the alkyl radical. This alkyl radical combines with another halide radical to form alkyl halide. Here the chlorine absorbs UV radiation and undergoes homolytic cleavage and forms chlorine radical. This chlorine radical is reacted with the methane and forms methyl radical. This methyl radical is again reacted with another chlorine radical to form the methyl chloride. So this is the one of the preparation of alkyl halides by using alkanes. And next one, we see another preparation that is from the alkenes. The alkenes undergo addition with the halogen acids like hydrochloric acid or hydrobromide, hydroiodide. And the alkyl halides, that means alkyl halides are obtained by addition of halogen acids of alkenes. Alkenes means an unsaturated compounds. Unsaturated compounds is treated with hydrochloric acid or hydrobromic acid or hydroiodic acid. These are called as halogen acids. Alkenes is on addition with halogen acids to form alkyl halides. Let us take an example. Ethene reacted with HCl to form ethyl chloride. It undergoes addition reaction, simply adding of H and Cl to the ethene molecule. If you take propene, is reacted with HBr. Here, double bonded carbon is an unsymmetrical double bond. It is a symmetrical double bond. It is an unsymmetrical double bond. Here, one side is containing of the two hydrogens, and other side it is containing of one hydrogen. So the HBr, the addition of HBr on these molecules depends upon the rule. If it is undergone a Marconi-Cuff rule, according to the Marconi-Cuff rule, the hydrogen is added to the more number of hydrogens. Double bond containing more number of hydrogens. And halogen is added to the less number of hydrogens. This is called as Marconi-Cuff rule. If it is an undergone anti-Marconi, the addition takes place in anti-Marconi-Cuff rule in the presence of peroxides, then hydrogen is added to the less number of hydrogens, and halogen is added to the more number of hydrogens. So these are the preparations of first preparation is from alkanes, and the second preparation from the alkenes. Now we will see the another preparation for alkyl halides from alcohols. Alcohols are nothing but hydroxy compounds. Hydroxy groups are hydroxy group of alcohols are replaced by halogen using halogen acid or phosphorus acid halides or thinyl chloride. Alcohols are nothing but hydroxy compounds. And ROH group, the general formula for alcohols is nothing but ROH group. The OH group containing compounds are known as alcohols. Its general formula is nothing but ROH. The hydroxy group is replaced by the halogen by treating with halogen acid or phosphorus halides or thionyl chloride to form alkyl halide. Alkyl halides are obtained by replacing the hydroxy group of the alcohol by treating with halogen acids or phosphorus halides or thionyl chloride or thionyl chloride. Let us see halogen acid. Alcohols is treated with halogen acids in presence of a dehydrating agent. Dehydrating agents like anhydrous zinc chloride or concentrated sulfuric acid to form alkyl halides. Alcohols, when treated with halogen acids in presence of dehydrating agent like anhydrous zinc chloride or concentrated sulfuric acid to form alkyl halides. Alkyl halides. Alcohols are treated with halogen acids. Halogen acids are nothing but hydrochloric acid or hydrobromide or hydroiodide is treated in the presence of dehydrating agents like anhydrous zinc chloride or concentrated H2SO4 to form alkyl halides. Let us take an example. Ethyl alcohol is treated with hydrochloric acid. Hydrochloric acid in presence of ZnCl2 or concentrated sulfuric acid to form ethyl chloride. Ethyl chloride. Or we can also prepare by treating with phosphorus halides. Alcohols react with phosphorus halides. Phosphorus halides are nothing but phosphorus trichloride or phosphorus pentahalides. Phosphorus trihalide or phosphorus pentahalide to form alkyl halide. That is a PCl3 or PCl5. Alcohol is reacted with PCl5 or PCl3. We are getting the alkyl halide. And also we can prepare from the alcohol by treating with the thionyl chloride in presence of pyridine, to form alkyl halide. Alcohols reacts with the thionyl chloride in presence of pyridine to form alkyl halides. Alkyl halides. So this is an example. Thionyl chloride is nothing but SOCl2 is treated with alcohol to form alkyl halide. Alkyl halide. When you see the mechanism for each of the reaction, first of all, we see the mechanism for alcohol reacted with halogen acids in presence of zinc chloride, anhydrous zinc chloride or concentrated sulfuric acid. So here, in alcohol, the OH is not a better leaving group, a pure leaving group, and Cl is not a good nucleophile, For enhancing the alcohol to the better leaving group, we are treating with the zinc chloride. Here, zinc chloride is activating the OH group is removing and replaces the chlorine replaces the chlorine and forms the chloroalkane or alkyl chloride, alkyl halide, haloalkane or alkyl halide. So in alcohol, the OH group, the oxygen containing a lone pair of electrons, these lone pair of electrons are donated to the vacant orbital of the zinc. Zinc containing the vacant d orbitals. These vacant d orbitals accepts the lone pair of electrons from the oxygen and forms a complexes like this. Here, zinc is accepting an electron, so it is acquiring the minus charge, and oxygen is losing the electron, so it acquires the positive charge. Oxygen is acquiring the positive charge, and the zinc is acquiring the negative charge. So the positive charge on the oxygen is an unstable, and it is converted into the OH ZnCl2, and carbocation is forming. This carbocation is reacted with the chloride and forms the alkyl halide. Here the H plus is removing. The H plus is reacted with the OH minus and forms the water molecule and converted again into the zinc chloride. So this is the one of the reaction to prepare the alkyl halide from alcohols. The next one, we can also prepare from the PCl chloride, phosphorus chloride halides, that is a phosphorus trichloride. When you're treating the phosphorus trichloride, the lone pair of electrons which is present on the oxygen is donated to the phosphorus. Then the electrons electrons are migrated from the phosphorus to the chlorine and removing as a chloride ion. Chloride ion. Here the oxygen process is unstable, so this takes the electron from the carbon and convert it to OHPCl, and this chlorine is reacted with the carbocation and forms the alkyl halide. Alkyl halide. Here another two chlorines are there, so again 2 moles of alcohol reacted to form alkyl halide, and 2 chlorines are replaced by hydroxy groups. Hydroxy groups. The same reaction is processed with another 2 moles of alcohol. 2 moles of alcohol, then we get the product like this. So next one, when you come to the PCl5, when you are considering alcohol is reacted with PCl5, phosphorus pentachloride. Here the lone pair of electrons which is present on the oxygen is donated to the phosphorus. Then the electrons are migrated from phosphorus to the chlorine atom and reveals the chloride ion, and forms the OH plus. OH plus is again unstable component. So these electrons, the carbon electrons are migrated to the phosphorus, and the chlorine is migrated to the carbon and forms the alkyl halide and phosphorus. Again, we see the mechanism for the thionyl chloride. The lone pair of electrons which is present on the oxygen is donated to the sulfur, and electrons is migrated from sulfur to the chloride ion and forms like this. Oxygen with plus charge is unstable, so it leaves as the H plus, and here it leaves as the Cl minus. The Cl minus is reacted with carbocation and leaves the sulfur dioxide and chloride ion. This chloride ion and HCl is converted to hydrochloric acid. So this is the mechanisms which is occurring in the reactions with the alcohol. While you are reacting alcohol with HCl or PCl5 or PCl3 or thionyl chloride, whatever it may be, we are getting the alkyl halide. Alkyl halide can be prepared from the alcohol by treating with the halogen acids or phosphorus halides or thionyl chloride So these are some of the preparations for alkyl halides. We have so many preparations. We have discussed about a few examples here. Next one, when you come to the physical properties, of alkyl halides, physical properties of alkyl halides. Lower alkyl halides are gases. Medium alkyl halides are higher membranes are the present smell liquids, and those beyond the 18 are colorless solids. Alkyl halides are polar in nature. They are soluble mainly in the organic solvents like alcohols, ethers, and benzene. When you burn the alkyl halides, the burns with the green edge flame. When you burn the alkyl halides, the burns with the green edge flame. The density decreases in the following order. That is from iodide is greater than bromide, bromide is greater than chloride, and chloride is greater than fluoride. When the boiling point also increases in the order of iodine is greater than bromide, bromide is greater than chloride, chloride is greater than fluoride. Alkyl halides are toxic in nature. Alkyl halides are toxic compounds, and they are used as an anesthesia when inhaled in the large amount. Produces general anesthesia when you inhale in the large quantity. When you are inhaling in the large quantity. When you come to the chemical properties, alkyl halides are very reactive compound. The reactivity of alkyl halides is due to the presence of carbon and halogen bond, which is highly polarized covalent bond. Because there is a greater difference between the carbon and halogen. There is a greater difference between electronegativity difference between the carbon and halogen. Here the carbon is having the less electronegativity and halogen is having the more electronegativity. So the electrons are migrated towards the halogen. So halogen is getting the negative charge and carbon is getting the partially positive charge like this. So when here halogen is a highly electronegative species, carbon is a less electronegative species. So the electrons are migrated towards the halogen and acquires the partial negative charge on the halogen and partially positive charge on the carbon. partially positive charge on the carbon. Here, the negative charged species, that is halogen atom, is facilitates to leave as halide ion. Then it is approaches the nucleophile, because the carbon is acquiring the positive charge, so it is reacted with the nucleophile. So there are two types of, the mainly alkyl halides is undergoing two types of reactions. Those are nothing but nucleophilic substitution reaction, and another one is called as elimination reaction. When you come to the nucleophilic substitution reaction, what is a nucleophilic substitution? Nucleophilic substitution reaction means the replacement of halogen by another nucleophile is known as nucleophilic substitution reaction. The replacement of halogen by another nucleophile is known as a nucleophilic substitution reaction. Your X is replaced by another nucleophile, so it is called as a nucleophilic substitution reaction. When you come to the elimination reaction, the removal of halogen is the alpha carbon atom, and hydrogen is removed from the adjacent carbon, that is a beta carbon, so it is known as alpha beta elimination reaction. So the halogen is removed and hydrogen is removed from the adjacent atom and forms the unsaturated molecule. So it is a elimination reaction. In our syllabus, we have only the nucleophilic substitution reactions. Nucleophilic substitution reactions. So already said that nucleophilic substitution reaction is nothing but the replacement of halogen by another nucleophile is known as nucleophilic substitution reaction. These nucleophilic substitution reactions are classified into the two categories basing on the mechanism. One is known as SN1 reaction, another one is called as SN2 reaction. SN1, one indicates the unimolecular, N indicates the nucleophile, S indicates the substitution. That means unimolecular nucleophilic substitution reaction. SN2 reaction means bimolecular nucleophilic substitution reaction. What is a nucleophile? Nucleophile is nothing but consisting of the two words. One is nothing but when you split up the nucleophile into two words, that is called as a nucleus and phile. Phile is derived from the Greek word. Is meaning is nothing but loving. That means nucleophile is a nucleus loving species. Nucleus means it is carrying the positive charge. That nucleus is having the positive charge. To attack the positive, it must have the negative charge. So nucleophiles are negatively charged species or electron-rich species. Nucleophiles are negatively charged species. That means it is an electron-rich species. Nucleophiles are basically electron-rich species which have the ability to donate a lone pair of electrons to the another species. And so it is nucleophiles are Lewis bases, because according to the Lewis theory, which is donating the lone pair of electrons is called as a base, which is accepting the electrons is called as an acid. Here the nucleophile having the tendency to donate the electrons, so it is a Lewis base. So the species which attacks where the electron density is less is known as a nucleophile. The species which attacks where the electron density is less is known as nucleophiles. These are two types. One is nothing but high electron density species, or we call it as Lewis bases. So these are nucleophiles are classified into the two categories. Those are nothing but charged nucleophiles, and another one is called as a neutral nucleophiles. Charged nucleophiles means the species which carries the negative charge are known as charged nucleophiles. The species which has the capability to donate a lone pair of electrons is called as a neutral nucleophiles. So we are discussing about unimolecular. In our syllabus, we have mainly about SN1 reaction, that is unimolecular substitution reaction. What is SN1 reaction? SN1 reaction, unimolecular nucleophilic substitution reaction. SN1 reaction. Here, the rate of reaction, which depends upon the concentration of alkyl halide, but not on the concentration of the attacking reagent, is known as unimolecular reaction. Unimolecular reaction. Unimolecular reaction. So these reactions mainly undergo tertiary alkyl halides mainly undergoes the SN1 reaction. SN1 reaction. Secondary alkyl halides follows the SN1 reaction when it is when we are using the polar solvent. When you are using the polar solvent. Primary alkyl halides does not involved in the SN1 mechanism. SN1 reaction. SN1 mechanism. The SN1 mechanism or SN1 reaction is mainly occur in the tertiary alkyl halides, but not in the primary alkyl halides. Primary alkyl halides. In secondary, when you are using a polar solvent, then undergoes the SN1 reaction. SN1 reaction. So SN1 reaction can take place in the two steps. SN1 reaction mainly takes place in the two steps. In the first step, the alkyl halide undergoes heterolytic cleavage. In the first step, the alkyl halide undergoes heterolytic cleavage and forms the carbonium ion. In the first step, the alkyl halide undergoes heterolytic cleavage and forms the carbonium ion. Carbonium ion. It is a very slow step, hence it is called as the rate determining step. In this step, only the substrate is there. That's why we are calling it as a unimolecular reaction. Unimolecular reaction. And it is labeled as SN1 reaction. In the second step, the carbonium ion reacts with the attacking reagent and combines to form a substituted product. It is a very fast reaction. Very fast reaction. In the second step, the formed carbonium ion combines readily with the attacking reagent, that is a nucleophile, to form the substituted product. It is a very fast reaction. When you see the mechanism, in the first step, oral reaction is like this. That means here, alkyl halide undergoes a heterolytic cleavage and forms the carbocation. This carbocation is reacted with the nucleophile and forms the product. When you see the mechanism in the first step, tertiary alkyl halide undergo heterolytic cleavage and forms the carbocation. This carbocation is readily reacted with the nucleophile, that is a OH minus ion, and forms the substituted product. Here, in the first step, the carbocation is a planar structure. Having the planar structure. So the nucleophile having the capability to attack from the both sides, from the front side as well as the back side. It is having the planar structure, so the nucleophile can attack on the carbocation from either from the front side or from the back side. So in this reaction, we are getting the racemic mixture is forming. Racemic mixture is obtained. That means equal and a retention configuration as well as inversion configuration is formed in the equal ratio. So it is called as a racemic mixture is obtained in this reaction. When you come to the another one, so this is an example. A few examples. That is a 3-chloro-3-methyl-hexane. 3-chloro-3-methyl-hexane. We are treating with all on hydrolysis. We are getting the racemic mixture product of alcohol. Like a 2-bromo-octane. 2-bromo-octane is another example for the SN1 reaction. When you come to the bimolecular nucleophilic substitution reaction, that is SN2 reaction. SN2 reaction, here the rate of reaction depends upon the concentration of alkyl halide as well as the concentration of the nucleophile. Here it depends upon the two components. One is the alkyl halide and another one is the nucleophile. So it is called as a bimolecular reaction. Bimolecular reaction. Bimolecular reaction. These reactions is mainly undergoes the primary alkyl halides. Primary alkyl halides mainly undergoes the SN2 reaction. SN2 reaction. Secondary alcohols, secondary alkyl halide, primary alkyl halides is mainly undergoes the SN2 reaction. Secondary alkyl halides undergoes SN2 reaction when it is a non-polar solvent. When it is a non-polar solvent. Tertiary alkyl halides does not react with the, does not undergoes the SN2 mechanism. SN2 mechanism. SN2 mechanism because it is having the cloudy nature. Cloudy nature. So SN2 mechanism involves here only in the one step. Only in the one step. So the nucleophile is attacked from the backside of the halide, backside of the halide. Because while the front side, the nucleophile is coming in the front side, the halogen and the nucleophile can repel each other or each other, so the product should not be formed. So the nucleophile is attacked from the backside of the halogen, backside of the halogen, backside of the halogen, and forms a transition state. That means the bond, the partial bond is formed between the carbon and the nucleophile, and the partial bond and partially leaving the nucleophile. When the nucleophile is entering into the component, entering into the substrate, the leaving group halogen leaves partially, and finally they're getting the substituted product. They are getting the substituted product like this. So the hydroxy group is attacked from the backside and forms the transition state like this. The partial bonds are forming between the hydroxy group and the halogen. After the strengthening of the hydroxy group, they completely leaves the halogen and forms the substituted product. In SN2 reaction, we are getting the inversion configuration. Inversion configuration. If it is, if you take R configuration, we are getting the product as S configuration. If you take the S configuration, we are getting the R configuration. D configuration, L configuration is obtained. L configuration, we are getting the D configuration. And the inversion configuration is obtained. In SN2 and SN1 reaction, we are getting a retention, mainly retention configuration is obtained. In SN2 reaction, we are getting the inversion configuration. Inversion configuration. We are getting so like this, it is a inversion configuration is obtained. So when you see the difference between SN1 and SN2 reaction, SN1 reactions are mainly undergoes the tertiary alkyl halides. SN2 reaction is mainly undergoes the primary alkyl halides. Order తీసుకుంటే, when you take the order of the SN1 reaction, is nothing but tertiary is greater than secondary, secondary is greater than primary. When you come to the SN2 reaction, primary is greater than secondary, secondary is greater than tertiary. Tertiary. Here the nucleophile is attacked from the backside as well as from the front side in the SN reaction. The nucleophile attacks only from the backside. Here the racemic mixture is formed. In SN2 reaction, a Walden inversion takes place. In SN1 reaction, the rate of reaction depends upon only the concentration of the alkyl halide. In SN2 reaction, the rate of reaction depends upon the concentration of alkyl halide and concentration of the nucleophile. Concentration of the nucleophile. Rearrangement is possible. Rearrangement is not possible. Not possible. Electronic factors influence the rate of reaction. Steric hindrance influence the rate of reaction. Steric hindrance influence the rate of reaction. So these are about the differences between SN1 and SN2 reaction. So this is about the alkyl halides. So the unit will be complete. Thank you.